Alright, so today we are doing intro to motion notes. So hopefully you got a chance to download the sheet, bring it into Notability, or download the sheet and print it off. And we're just going to kind of fill it out as we go. Across the top it says term, symbol, units, definition, and equation. And then we're just going to kind of fill in as we go. And I would say always keep these intro notes, especially for college, because this is the first unit you'll start with if you do take college physics. Alright, so kind of nice, but for scalar quantity, no symbol, no units. And it says definition, a quantity that has only magnitude. So definition, a quantity that has only magnitude. And there's no equation for this, but we do have an example on the right side there. It says, example, if you told somebody you're going to run 10 miles, you're telling that person the magnitude or the length of your run. So in that case, the 10 miles, that number is what's considered in physics a magnitude. You didn't say anything else besides the quantity of miles that you're going to run. That's a lot of miles, by the way. Alright, vector quantity. This one does have a symbol. It's an arrow. So I drew a purple arrow there. So anytime you see an arrow in physics class, or actually in calculus class as well, they use that arrow to mean that that quantity that you're talking about is a vector quantity. There's no units for a vector quantity. But the definition says it's a quantity that has both magnitude and direction. So a vector quantity is a quantity that has both magnitude and direction. And just to kind of go back to our example from before, if you said I ran 10 miles, that's a magnitude, so that's a scalar quantity. But if you said I ran 10 miles west, as soon as you put that direction on there, the direction makes it become a vector quantity. So if you have a number with a direction in physics, in calculus, that's considered a vector quantity. All right, term number 3, distance. And I'm just going to make a note below each term if it's a scalar quantity or a vector quantity. So for distance, it's a scalar. The symbol we use is same as you'd probably use in math class. You use a lowercase d for distance. The units that we use in physics are going to be usually meters, sometimes miles. And then distance is just how far in length an object travels. And the example I put here, lowercase d, distance is equal to 15 miles. So maybe you're going jogging. I don't know why I'm saying jogging because that's a long jog. But let's say you travel the distance of 15 miles in your car. Notice since distance is a scalar, then that means we need just the magnitude of the distance traveled. So you just say, oh, it's 15 miles, but you don't give a direction. And then again, if I ever go too fast, feel free to pause before you go on to the next one and just copy it into your notes. All right, term number 4, average speed is a scalar. You might think you'd use an S for average speed, but our book does not do that, and most physics books do not do that because when you use an S, it tends to look a lot like the number 5, so it can be confusing. So what they do instead is they use a V, kind of interchanging it with velocity, and they put a bar over the top of it, or a line, so that, just like math class, when you put a bar over the top of something, that means average. So average speed, and the units are going to be meters per second, or miles per hour. Sorry, it's kind of, my letters kind of bled together there, but usually meters per second. And then it just says how far an object travels divided by the time it takes. So basically it's the rate at which you're covering distance. And we actually do get an equation over here. So average speed, you just take your total distance divided by your total time. And I'm just going to make a note of this here. It's going to be total distance over total time. All right, and again, if you go too fast, hit pause. Term number 5, position, is going to be a vector quantity. So that means it's going to have a number with a direction to it. The symbol we use for position is an X. And then since it is a vector quantity, we put an arrow above it, which means that whenever you give your position, you're also going to have to include the direction. So the units for position in physics land here is going to be meters, usually, sometimes miles. And it says it's just an object's location in space. So we start in 1 dimension, so you can picture being a kid back in elementary school talking about like the X number line. And that would be 1 dimension because you can move side to side basically in the positive or negative X direction. And that would be 1 dimensional. And then eventually when you took math classes later on, then you could get into 2 dimensions where you could move some dimension in the X and then some dimension in the Y. But we actually live in a 3-dimensional world, right? So you basically eventually you're going to have X, Y, and Z. So X, Y, and Z would be your 3 dimensions of space, and then a 4th dimension of time. But that gets pretty confusing pretty fast. So we're just going to say, hey, position for right now, it's going to be some position in 1 dimension, and that dimension is going to be X. And we said here, X position is a vector, so we put the vector symbol above it. And then we said plus 4 feet. So maybe you're thinking about, I'm going to move 4 feet forward and take a few steps forward. That actually does have a direction to it, because when you say the positive direction or forward, that gives you your direction. And then your magnitude, the how far, is just 4 feet. All right, and then we go into 6. So we had number 5 is position. Now we go into something called displacement, which is again a vector. And this one looks a little more confusing, but with some examples, you'll see it's not too bad. So we have X, so it's position from before. And then we have a Greek letter, and this is a delta. And I'm just going to make a note of this here. When you see delta in physics or in math and calculus, that means changing. So when you see delta, that means change in X. So it's the change in an object's position. So when you see delta X, that means change in position, or we just shorthand it to say it's displacement. And the equation for displacement, so you're going to see it looks like triangle X over here, is this to take your final position minus your initial. And that'll tell you how much your position changed. And again, I feel like when you do these examples, it'll make more sense as we go along. All right, number 7, average velocity. We're going to use V again for velocity. This time, we had average speed before, which was a scalar. But average velocity is a vector. So I always just think velocity vector. V, velocity vector. All right, so the units are meters per second, or miles per hour. And then now the definition for average velocity is an object's displacement per unit of time. So now we say, okay, so we have average velocity, you take an object's displacement. Remember, displacement was the symbol delta x. So our equation for average velocity is just going to be your change in position or displacement divided by time. And some people out there might think, well, isn't that the same as average speed? And you can see, no, it's a little different, because average speed up here, average speed is just your total distance traveled over total time, where average velocity is your change in position or your displacement. So let's say your displacement over time. And then our last term on our little chart here is instantaneous speed or velocity, and that's a vector. So again, we're going to use this letter V for velocity, and then since it's a vector quantity, we put an arrow above it. Units are meters per second, or miles per hour. And then it's the speed at one specific moment in time. And then I put for equations coming soon, because we'll actually do quite a bit with the equations for instantaneous velocity. But for right now, we're just going to leave that one kind of TBD. All right, and so a good example that I like to think through that kind of helps me like picture this in my mind's eye, it says, example, what does a speedometer in your car measure? So you can see I just added that little question in there. So of all these terms we just kind of went through very quickly, what does a speedometer in your car measure? So take a second, hit pause, and then think that through. The speedometer in your car measures the speed or velocity at one moment in time. Actually, it measures the speed at one moment in time. So it's measuring the speed at one moment in time, so it'd actually be measuring your instantaneous speed. In the speedometer, or if you read it, speedometer, the speedometer measures the speed at one moment in time, but it doesn't measure the direction. So that's why it's called a speedometer, because we said for speed is a scalar quantity. So I'm just going to say speed is a scalar. It just gives you the number. The speedometer doesn't tell you anything about the direction you're traveling. So not that you guys break the law on speed, but if you were speeding, say you're going past like Valley Middle School and Garden View there, does a police officer, if they pull you over and you're speeding, do they care about your instantaneous speed or your average speed? So think about that for a second. If you get pulled over for speeding, does a police officer, are they writing you that ticket for speeding because of your instantaneous speed or your average speed? And hit pause if you want to think about it. Well, hopefully you said that the police officer, basically when they're doing their radar gun, they're taking your speed at some moment in time. So they can actually write you a ticket if at any instant, at even just the slightest moment in time you went over the speed limit, they can write you that ticket. And maybe they pull you over and they say, do you know how fast you're going back there? And you're like, well, on average, I was going maybe 25 miles per hour, right? Maybe you were driving pretty responsibly, and all of a sudden, for a split second, you stepped on the accelerator, and you got up to a high speed. Well, the police officer doesn't concern themselves with your average speed. They say, hey, at some moment in time, you're going above the speed limit, and I'm going to give you a ticket. Yeah, so that's the way I like it. You look at your speedometer, that gives you your speed at some instant in time, whereas your average speed would be your speed over like the whole length of your trip. All right, we'll do one example together, and then I'll just put up the answers for the rest here. But example number 1, it says, as a confused 9th grade student, Freddie Physics walked 20 feet east to his science classroom, then 5 feet east to the drinking fountain, and then 10 feet west. The whole trip took 20 seconds. What is his distance traveled? What is his displacement? What is his average speed? What is his average velocity? Hint, draw a picture of Freddie's trip on the grid below using vectors. And so vectors are just going to be arrows. So take a moment, hit pause, try this one out, and then we'll come back and kind of talk it through. All right, so on my grid here, basically Freddie had 3 parts to his trip. I always label never eat soggy waffles, so north, east, southwest. So always do that just so you don't make a silly little mistake. But 20 feet east, so I said 5, 10, 15, 20. And then it said he went another 5 feet to the drinking fountain. And then he went 10 feet west, so 2 squares back. So I just circled, he ended up right here where I circled. So there's Freddie Physics. And they want to know distance traveled. So for distance traveled, I just made myself a note. And this is not difficult. So if you're like, why is Mr. Ryan going so slow through this? It's just to kind of get down the groundwork for when we do more difficult things. Hopefully you're like, oh, this makes sense because we did the easy examples. But total distance, you just add up the different parts to his trip. And he went 35 feet. And distance is a scalar, so it didn't say anything about the direction that he traveled. But displacement's going to be a little different. So displacement says, hey, your change in position is just your final position minus your initial. Well, his final position over here, he's 5, 10, 15. He's at 15 feet right here. So XF is 15 feet. Well, X initial, XI, is equal to 0. So if you take your final, he was 15 feet east minus his initial 0. So that means he was displaced 15 feet east. So this is kind of like why you're tired at the end of a school day, right? Because your distance might be 35 feet because you might go forward, go backward, go forward again, whatever. But you're not actually displaced that much. So sometimes you walk around the school looking for a classroom, but your distance is very high, but you actually didn't cover much ground, is basically what that's saying. A good example would be like at the end of the day, you always return back to your home, right? So at the end of the day, your displacement from where you start and end of the day is probably 0 because you're probably sleeping in the same spot that you wake up in the morning, right? But your total distance you travel throughout the day might be very great. So distance and displacement are definitely different things. All right, and then we look at average speed. So we say, well, average speed is the distance that Freddie traveled divided by time. So 35 feet over 20, so it's 1.75 feet per second. So average speed for Freddie is 1.75 feet per second. It's a scalar, so I don't have to put any any direction on there. And then average velocity is different because average velocity is going to be your displacement divided by time. So in this case, he was displaced 15 feet east. It took him 20 seconds. So his average velocity is going to be 0.75 feet per second east. So because he's kind of going this, not a straight line path here, he goes forward, backward, his average speed and his average velocity are not going to be the same. So that's where we start to talk about it. I would say we're going to pause there, but definitely keep these notes because someday if you take college physics or maybe you're taking a physics class again, it's nice to go back to these kind of beginner examples. So I always say keep these notes because this is the kind of stuff when you do take college physics, you'll start with in college. All right, go ahead, try the backside. I'm just going to post the answers. So try all of them on the backside, and then when you're ready, go ahead and hit play again, and then the answers will be there for you to check off. Okay? All right, have a great day. Go Physics All-Stars.